term rational expression is just a fancy way of describing a fraction that has variables in it. The more formal way to describe it is to say that it's the quotient, meaning you're dividing two polynomials. Now, just like with regular fractions, we have to write them in simplest form, which means we're going to have to see if there's any reducing that we can do. And if there's any addition or subtraction in either of the expressions in the numerator or denominator, we're going to have to do some factoring. Now in this first one, there's no addition or subtraction, so we can just jump straight into the reducing. And so for the numerical part, the 18 and the 60, we just need to find something that divides evenly into both. In this case, the biggest number that divides evenly is 6, so I can divide 6 into 18 and get 3, and then 6 into 60 and get 10. If that wasn't the biggest number, then I would see that I could do some more reducing. But then I also have to reduce the variables. And so for that, I'm just going to use my exponent rules. So when I have the same base and I'm dividing, I'm just going to subtract the exponents, and wherever the larger exponent was, that's where my answer is going to go. So in this case, I have the 3 on the top, the 10 on the bottom, and then if I subtract these exponents, 5 minus 2 is 3, the bigger exponent was on the bottom, so we're going to end up with x to the third on the bottom. So our answer is 3 over 10x to the third. In the second example, now we might be tempted to see those x squareds and want to reduce those, but we can't. One of the rules for reducing rational expressions is that you cannot cross cancel, you cannot reduce things that are connected by addition or subtraction to other terms. You can only reduce things that are connected by multiplication. And so that's why we're going to have to engage in factoring for these types of expressions. So for the numerator, there's nothing that I can really do there for now, so I'm just going to leave that as 2x squared. But for the denominator, I need to look to see what I can factor from both those pieces. What can I undistribute in this case? And so the only thing that we have in common between those two terms is an x. So I'm going to undistribute an x, and now I need to see what's left behind inside the parentheses. So x times 3x would get me back to 3x squared, and then minus 4, because x times negative 4 would get us back to the original negative 4x. And so now that I have it factored, I can see if I can do any reducing. And because this x is now connected by multiplication to that entire set of parentheses, I can reduce that x with the x squared that's up in the top. And so I'm going to cross out the x down here, and then I'm going to knock this down to just being x to the first. I'm basically just subtracting the exponents, 2 on the top, 1 on the bottom, to end up with just a single x in the top. And so now at this point, that's all that we can do. We end up with 2x over the 3x minus 4 that's in the parentheses down on the bottom. And again, we might be tempted to reduce this x with the x that's up top, but because this term 3x is connected by subtraction to the 4, there's no more reducing that we can do. We can only reduce things that are connected by multiplication, not by addition and subtraction. The next problem has a similar trap of tempting us to reduce when we can't, like the previous question. So for example, the x on the top here and the x squared on the bottom. We may think that we can reduce those, but because the top x is connected by subtraction to the minus 4, those essentially come as a package deal. The x minus 4 are connected to each other through that subtraction, and so we can't reduce the x with the x squared on the bottom. And since there's no factoring to do on the top, and the x squared, there's nothing to do with it, our answer is just what we see given to us. This expression is already in simplest form. For the next one, we definitely have some factoring that we can do on the top. Hopefully we recognize that x squared minus 9 is a difference of squares. So I'm going to factor that expression into x plus 3 times x minus 3. The x times x will get us back to x squared. The plus 3 and minus 3 multiplied will get us back to the minus 9. And then because those are opposite signs, the inner and outer terms, if we were to refoil, would cancel each other out. So we factor into this pattern. Now on the bottom, we have this 3 minus x, which looks an awful lot like the x minus 3 that we have in the top. It's just reversed. And so this is actually something where we are going to be able to do some more factoring and then reducing. And the trick that we're going to have to use is we're going to have to factor out a -1 out of the denominator. So we want to reverse the order of the subtraction. And so the way that we can do that is if we still have the x plus 3 and the x minus 3 on the top, I can factor out a -1, and that will have the result of flipping the order of the subtraction in this expression in the denominator. So now instead of 3 minus x, it'll turn around and be x minus 3. And if we were to redistribute that -1, I think we'd see that that would get us back to this expression here. -1 times x is -x. -1 times -3 would be +3. So this is a trick that we can use when we see two terms like this one and this one that have the same elements, are just reverses of each other in terms of the subtraction. So if we factor out this -1, now we do have a common term in the top and the bottom. So this entire factor, this entire x minus 3 that's in this set of parentheses can be factored out, since it's connected by multiplication to the x plus 3 in the top, and it's connected by multiplication to the -1 on the bottom. And so then our end result here, we end up with just x plus 3 on the top over -1 on the bottom. And so we could leave our answer like this, or we could go ahead and divide both parts of the expression by -1 and write our answer as -x minus 3. So either one of these answers would be acceptable. But the key here on this one is understanding this idea of when we have these two terms that have the same elements, they're just reversed in the order of the subtraction, we can factor out a -1 as a trick to flip one of those subtractions to make it so that we can reduce. In this next example, there's a lot of tempting elements that lead us to think that we might be able to do some reducing right away. The x squareds are tempting. We've got these negative and positive 12s, the x's in the middle, but we can't do any of that. We have to factor these expressions first and then see if we can reduce some of these factors, because all of these elements, the x squared and the x and the minus 12 on the top, and the x squared and the 7x and the 12 on the bottom, are connected to each other by addition and subtraction, which means we can't reduce. So we need to factor. So up in the top, I'm going to set up two sets of parentheses. On the bottom, I'm going to set up two sets of parentheses and use my reverse FOIL to factor these. So for the top, I'm going to have x, of course, as the first piece in each set of parentheses. I'm multiplying to make a -12, so I need a positive and a negative. And I need to multiply to make -12, but add to make 4, or 1. So the two numbers are going to be 4 and 3. And so we see that 4 times -3 is going to make -12, but 4x minus 3x will give us the positive x that we need. For the bottom, again, x is the first piece in each set of parentheses. This time we're multiplying to make a positive, and we're adding to make a positive, so I need two positives. And again, 4 and 3 are going to be my numbers that multiply to make 12 and add to make 7, so I can go ahead and fill those in. So now that I have everything fully factored, now I can look to see if I have any common factors between the top and the bottom. And indeed we do. We have the x plus 4 on the top and on the bottom. I can go ahead and reduce those. And they don't even have to be stacked directly on top of each other. We could have had the reverse order of these two and I still would have been able to reduce. Now, for the remaining part of the problem, the x minus 3 and the x plus 3, those we cannot do anything with them. Unlike the previous question where we were able to factor out a -1, if we were to factor out a -1 from the top, it would reverse it into 3 minus x, which still wouldn't be the same as the bottom. And then factoring out a -1 from the bottom won't turn it into x minus 3, it'll turn it into -x minus 3. So at this point, we've done everything that we can. X minus 3 over x plus 3 is our final answer. And as tempting as it is to think that we can reduce the x's or reduce those 3's, because they're connected by subtraction and addition to each other, we cannot reduce. We have to just leave our answer as is. For the last one, we've got the top that we're going to have to factor. Now I see it's x cubed and x squared and x. So before I start doing my reverse FOIL and break it into two sets of parentheses, I'm going to undistribute an x from the top. That leaves me with x squared minus 10x and then plus 25. Now on the bottom, hopefully we're recognizing that as that difference of squares that we saw in a previous example. So I'm going to break that up into x plus 5 times x minus 5. Now I have some more factoring to do on the top. I have to work on this trinomial here, this x squared minus 10x plus 25. So I'm going to still have that x out front, but now I'm going to set up my two sets of parentheses for the rest. And then I still have x plus 5 times x minus 5 in the denominator. So for that numerator, x and x are going to lead each of the sets of parentheses. I'm multiplying to make a positive 25, but I'm adding to make a negative 10. So the only way I'm going to have that happen is if both these numbers are negative, and so hopefully we see that the two numbers are going to be negative 5 and negative 5. Negative 5 times negative 5 is positive 25, and then negative 5x plus negative 5x will give us our negative 10x. So now I'm ready to do whatever reducing I can, because everything in the top is now connected by multiplication, as are the two pieces on the bottom. So now I'm free to reduce. So I've got these x minus 5s that are in common in the top and bottom, and then that's it. The x minus 5 and x plus 5 are like the x minus 3 and x plus 3 from before, where they're not similar enough for us to be able to reduce, and we have this extra x that we can't reduce either. So our final answer on this one, and we can either distribute the top or we can go ahead and leave it as is, x times x minus 5 over x plus 5, or if we want, we can distribute and write x squared minus 5x on the top over x plus 5 on the bottom. Either format of the answer in this case would be just fine.